explaining the quadratic function.
Welcome to this explainer. Today, we're going to look at math through a completely different lens. Instead of just memorizing endless formulas, we're going to tackle exercise 1.1 of your graphical representation of functions unit by treating math, well, exactly like a detective solving a mystery. You see, every single curve on a graph actually has a hidden identity, a highly specific algebraic equation that belongs to it and only it. Our job? Uncover that identity.
So here's our agenda for today. We'll start with the graphing mystery, look at the intercept equation, track down clue 1, finding intercepts, then clue 2, the specific point. After that, we're solving the equation, and finally wrapping up with your 3-step math blueprint.
All right, part 1, the graphing mystery. Looking at an abstract graph can feel pretty overwhelming, right? You see this sweeping U-shape or an upside-down parabola, and honestly, it just looks like a random line on a grid. But if we totally change our perspective and treat that graph as our primary suspect, we can start hunting for specific, undeniable visual clues that reveal its true mathematical identity. It's really all about knowing exactly where to look.
Moving on to part 2, the intercept equation.
To solve this mystery, we're going to need the right magnifying glass. And in our case, that's this incredibly powerful formula, the intercept form of a quadratic equation. It reads f of x equals a times x minus h times x minus k. Just think of this equation as the skeleton of our function. The letters h and k represent the exact spots where our graph crosses the horizontal x-axis. And that letter a, that's our scaling factor. It tells us whether our curve opens upwards or downwards, and just how wide or narrow it is. So all we have to do is find the numerical values for h, k, and a from the graph to totally crack the case.
Which brings us to part 3, clue 1, finding intercepts.
Let's dive right into a real case file from example 3 to gather our first set of clues. Look closely at exactly where this blue, upside-down curve actually crosses the horizontal line, the x-axis. You can clearly see it hits at 2 distinct locations, at -1 and at +1. Now, these aren't just random dots. They are our h and k values literally hiding in plain sight.
As the textbook solution outlines for example 3, these visual intersection points hand us our first really solid mathematical clues. We can extract that h equals -1 and k equals +1. Boom, we already have 2 of our 3 missing pieces. By plugging these h and k values into our intercept formula skeleton, we successfully build the foundation of our equation. Notice the algebra here though. Because our formula is x minus h, subtracting a -1 actually becomes x plus 1. It's a great example of how visual coordinates translate perfectly into algebra. We now have y equals a times x plus 1 times x minus 1.
But hey, every good mystery has a twist, right? Here it is. Just knowing where the graph crosses the axes is not enough to identify it completely. Think about it. There are infinitely many curves that could pass through those 2 exact intercepts. Some could be super tall and skinny, others really short and wide. To lock down the exact identity of this specific curve, we absolutely have to find that missing a value.
So let's find it in part 4, clue 2, the specific point.
To find that missing a, we need to go back to the scene of the crime, our graph, and find one more crucial piece of evidence. If you examine the graph again, you'll see we aren't just given the intercepts. There's another perfectly clear, explicit point labeled right at the very peak, or the vertex of the curve. It is the coordinate 0, 4. This means when the x value is 0, the y value is exactly 4. And this single coordinate, it's the key to unlocking our mystery.
On to part 5, solving the equation. Now we take all the clues we've gathered, our skeletal equation and our specific point, and put them together in the interrogation room to force out the final answer. The way the textbook handles this is honestly a thing of beauty. We take our specific points x and y values, 0 and 4, and we just substitute them straight into the equation we built earlier. Where there was a y, we write 4. Where there was an x, we write 0.
Look at what happens to our equation when we do this. By replacing x with 0 and y with 4, we get 4 equals a times 0 plus 1 times 0 minus 1. We have successfully isolated a as the absolute only unknown variable left in the entire equation.
From here, it's literally just basic arithmetic. 0 plus 1 is 1. 0 minus 1 is -1. 1 times -1 is -1. So our equation simplifies all the way down to 4 equals -a. Multiply both sides by -1, and a quick simplification reveals our final missing clue. The scaling factor a is exactly -4. And hey, that negative sign perfectly matches our visual evidence too, since we know an upside-down curve has to have a negative a value. Substituting our newly found back into our skeleton gives us this final, undeniable mathematical identity for our suspect curve. Y equals -4 times x plus 1 times x minus 1. If you expand those brackets, just like the textbook's derived solution shows, you get y minus -4 times the quantity x squared minus 1. Case closed. The visual curve has been completely 100% decoded into algebra.
Finally, Part 6, your 3-step math blueprint. Let's step back for a second. We didn't just solve one isolated math problem today, we actually uncovered a universal method. This is your ultimate 3-step blueprint for graphical representation. Whenever you face a curve in exercise 1.1, just follow this checklist. Step 1, find your h and k by looking at the x-intercepts. Step 2, plug in one other specific, clear point from the graph to give you a temporary x and y. Step 3, use that temporary x and y to solve for a, and then rewrite your final equation. It really is that systematic.
Let's see how this builds your confidence by looking at another example from the text. Whether you're looking at the tall, upside-down curve from example 3 or a completely different right-side-up curve from example 4, you don't need to panic. The specific graphs look totally different, sure, but the underlying investigative process, it remains exactly the same.
As we can see in the text solution for example 4, it follows our blueprint to the letter. After finding a new a value, which actually happens to be +2 in this case, the exact same logic of substituting that solved a value back into the intercept equation is used. That gives us the final answer of y equals 2 times the quantity x squared minus 3x plus 2. The numbers change, but the detective work is identical.
By shifting your mindset from strict memorization to active investigation, these problems go from frustrating to highly satisfying. With this simple, structured 3-step toolset in hand, every abstract graph in exercise 1.1 isn't some huge wall blocking your path, it's just a mystery waiting for you to solve it. So, open up your book, look at the very next graph in the exercise, and ask yourself, what are the clues telling me? Thanks so much for joining me on this explainer, and happy decoding!